Okay, this is entry 2 of my mathematical diary or journal. I'm sticking with journal just because, well, just because I made that thumbnail, but this is entry 2 of it. This time, I'm going to recap what I did last time because I wasn't really very happy with how I explained everything last time. I will introduce fields and ring homomorphisms and polynomial rings. I had a couple more things to go over this time, but I think that this is plenty, especially given that my my aim is half an hour, which I'm not sure, but we'll see. If it's shorter, then it's shorter. But okay, in the intervening time, I haven't done much mathematical learning. However, this none of this is new to me. I have ordered these two books, which not cheap, but it was recently my birthday, so and worthy investment, I guess. Um, the first is some sort of preparatory book for learning the algebra that is specifically used within algebraic geometry, and the second is a very comprehensive book in what's called modern algebraic geometry. I've seen it. I've seen algebraic geometry be split into three stages. So there's classical, there's modern, and there's, I guess, contemporary, but like double modern. What's being done now? However, algebraic geometry is not written contemporaneously, but written somewhat contemporaneously to the uh, beginnings of the modern algebraic geometry. So it's a summary of a lecture series given by an absolutely incredible mathematician called, I've forgotten his first name, but a Mr. A. Grothendieck, I think it actually is, which is Grothendieck, who thought of a very large amount of things, but it's also based on Leray. I think he invented sheaves while in a concentration camp in World War II. Um, Grothendieck used sheaves. He is one of the brains of the 20th century, in my personal opinion. There's also people like Milne, Serre. Oh my goodness, what on earth is he? There's so many, but I don't remember a lot of them. But Grothendieck, uh, Eilenberg, I think, is one of the others. Saunders MacLean. Moving on. I've uh, I've gone on a bit enough about this, but I'm waiting on these two books. They are apparently being printed for me and will not arrive within a week or two, but that is the price that you pay for ordering, well, on top of the price, which is not cheap. But a set, from last time, a set is some thing containing points. So sets are usually described with set builder notation, which is line 3 here. Where you start with a big curly bracket and then you declare this is what the set contains. This is what elements of the set look like. Then you put a colon and then you describe it. If you have some sort of finite set, then you can literally just write like 1, 3, 5. That is a finite set. And you can relate any two sets by their union, basically set addition, their intersection, which doesn't have a nice, neat analogy in terms of the arithmetic operators. But then you have what's best described as set multiplication, and this, if you aren't within university level maths, you'll often see multiplication written. Let's actually do this properly. You'll often see multiplication written not with a times symbol, but with a cross, but with a dot. So 9.3 equals 27. Or if not if they're numbers, but if they are, say, x and y, then you'll just write them like xy. That's x times by y, which isn't as confusing as it might seem upon a first glance. In fact, that's the most common way of doing it because it's just easier. There's less things to do. But this is why you don't see times. So, as stated last time, there's two ways of visualizing this. Firstly, there's the way of literally visualizing it. So, think of this as real times real, and this is like here, this is over here. Oh look, this is 1, this is 3, 1 comma 3. However, this is called real squared because it's real times real. However, what if this is real squared? There's no visual intuition here. What if it's real cubed? What if it's the Hamiltonians? What if it's this or that? It's that should be in red probably. Oh goodness, that should be in red probably. Because you've not been introduced to it, and I probably won't introduce, so it will probably stay red. If you're interested, just look up quaternions. So quarter, neon. But given two sets, you can add, you can see the bits which they share, or you can multiply them. And this is how you write that in set builder notation. Sort of. There should be an or there. So things which you put before the commas, you put before the colons things what this set yeah, what this set contains, what it looks like. And then after the commas, you put the statements. So this might seem like a contradiction to what I just said, but what this looks like is elements of S, such that elements are also in T. But a lot of maths and a lot of the the I don't know how to say the intimidation factor of maths is in the notation, and if you read it aloud, it seems completely natural. So, uh, S, the Cartesian product of S and T, are pairs of S, pairs such that the first one is in S, the second one is in T. Then I introduced functions, which are maps between sets. So it's an assignment of elements of S, or elements of X here, into Y. So every element has an assignment. Not necessarily every assignment, every Y can be assigned to. So, oh, if I recall, I said that within the last entry. So, for instance, x equals y squared. Well, any of the within the real numbers. Any of the bits down here don't really work because you can't square a real number to get a negative real number. So this here is how it's written. So f maps x to y such that x is mapped to f of x. Or x is mapped to, or so that, but it means the same thing. Then I introduced rings. So a ring is a generalization of the the integers. So it's somewhere where you can add and you can multiply. So these are the addition. It doesn't matter which direction you put them in. You can sort of squish them down into pairs without breaking anything. The interesting one is here. So if I recall correctly, I did do this visualization, but I'll do it up here. If you have a square of side length a plus b and a side length c plus d, well, if I split this up into c, d, and maybe over here a, b, so b times c, a times c, a times d, and b times d. These two are the same, and that's a fundamental property of rings. I don't know if there are any algebraic structures on which that isn't the case. Of course, ones where there are two different operations. I will probably. I'm going to write that down and see if there is any. Non-distributive. Yeah. Alg structures. So, examples of rings are the integers. Oh goodness. The integers, the matrices over some field, which we will get to that in not the next slide, but the slide afterwards. And then we have zero identity identity. So the identity maps the pair which is 0, 0 into 0. And this is a ring. In fact, it's a special ring. It's sort of the complement to the Z ring, which we will see when we introduce ring homomorphisms. And we will also see this. This is a univariate polynomial ring. but it's red R, so R is a ring, adjoin X, and that times is kind of bugging me, so one moment, let me... Ooh. Yeah, that times is bugging me. I can't erase things which I've already written previously, so dot, not times. So, I could do R adjoin alpha, but it means the same thing, but we will get to this. Oh, and a ring is commutative if this symmetry property of addition, called commutativity, is holds. So obviously within commutative algebra, every ring is assumed to be commutative. I assume. We will see. But before we get into it, last time I asked if this assignment to the integers of an addition and a multiplication, not the normal multiplication, is a ring. And that is no, it is not a ring. So, oh, and I called it that just to distinguish it from the regular times, but it means the same thing. It doesn't matter whether or not I draw an elephant to describe it. But here you can see distributivity. So it is a ring if this is equal to this. Remember? Back here, this bit. That's called distributivity. Well, by just simply expanding it out using the definitions, you can see the left-hand side is this, the right-hand side is this, and they are not equal. In general, they are equal when a plus b plus c plus d equals 0, but not in general, so a, b, c, and d is 1, then no. So, yeah, it isn't the case. So, we move on to new things. First of which is a field. Now, a field, we're not going to spend very much time on this. It's a commutative ring in which everything is divisible. I should add commutative up there, but I don't know. I think there is a definition of a thing where you don't assume commutativity. I forgot what it's called. I think I'm not sure. I know that there is definitely something where you don't assume that it's commutative, but then division goes weird. You have a left inverse and a right inverse. It's very odd. But a commutative ring is a ring, sorry, a field is a commutative ring such that almost all elements are divisible. And I have just seen a mistake. So, you have the regular ring axioms, so this, these two, well, this is not necessarily an axiom, but I will do this in a different color. The circled ones are axioms. I'll do it in purple. This, 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 and this. But not this, this, and this. So the additions are 1 can't be equal to 0 because otherwise division would be weird. A A times B is B times A, because otherwise division would also be weird. You would have A for any element, you would have two different inverses depending upon if it goes on this side or this side. It's kind of odd. I don't need to worry about that because I'm going into commutative algebra, and I will only explain commutative algebra. So ha. um, but 1 is not equal to 0. A times B is B times A, and every element has a multiplicative inverse. Every non-zero element has a multiplicative inverse. That's important, because otherwise you'll be dividing by 0, which I'm not able to do. Oh, and fields are usually written K. That's because they started out as, I think that's how you spell it, but they started out as a German word which begins with K, which I'm not going to try and pronounce because that's, I think, like an noise. So Körper, Körper. I don't know. Correct me if I'm wrong. In fact, one of the people who is holding me to account for making these speaks German, so she can hold me to account. How do you pronounce that word? So, the prototypical example of a field, just like how the prototypical example of a ring was the integers, is the rational numbers, which is just the integers plus some extra rules or some extra elements. So you just start with the integers and then you just add the inverse of every element, which we will see later is a construction. Oh, and this is the finite field of two integers. So 0, 1, 0, 1 plus 0, 1, 1, 0 times 0, 1, 0, 1, 0, 0, 0, 1. This can actually be an exercise. Prove that that makes a so prove that 0, 1 plus times is a field. One hint is that 0 represents odd numbers and 1 represents even numbers. Sorry, 1 represents odd numbers, 0 represents even numbers. I am a silly sausage sometimes, but we like fields because they tend to have nice properties. Not all fields have all nice properties, obviously. Some have nicer properties than others, so the complex numbers are just nicer than the real numbers. So those who already know a little bit of algebraic geometry, or for some reason those who are rewatching this, I'm pretty sure Hilbert's Nullstellen. This should be in red, but Hilbert's Nullstellensatz, I think, is how it's pronounced. But that requires an additional property called algebraic closure, which we will come to. Nullstellensatz. So this is just a fun fact, but every module over a field is a vector space. That's just the definition of a vector space. Every module over a field is a free module. which means that it has a basis. So it has an x1 dot 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 xn such that any m is the linear sum of r equals 1 to n a n x n such that a n is in M, but M is a module. But we're not worrying about that right now. But every module over a field has a basis, whereas every module over a ring doesn't necessarily. So, for instance, the modules over the integers is all abelian groups, which all possible versions of this, this, and this. Which is not as easy as studying vector spaces, which are field modules. Which, I mean, the first one you learn in first year of a maths degree, and it's basically not talked about. Not taught really again because it's so easy. But so within my current year in my degree, 3 out of 4 of my modules are all based upon the notion of this is a very difficult task. It would be a much easier task if we changed our perspective to linear algebra, which is the study of vector spaces. So that's representation theory and Riemannian geometry, which is a very similar field to algebraic geometry. It's not the same thing. We're talking about similar things, so sheaves, for instance. But another one is called functional analysis. A lot of that is based upon linear algebra. A lot of basic, a lot of high-level maths is built around the principle of this is a very difficult problem. How do we change it to linear algebra to solve it easier? Which representation theory is that for groups, and Riemannian geometry is not necessarily that for just arbitrary, arbitrary smooth manifolds, but it does hinge on a lot of vector space theory in almost all of its definitions. But the next thing which I want to introduce is ring homomorphisms. So a ring homomorphism comes from the Greek homo, same, as in certain words, and morphism, meaning shape. So it preserves shape. On each side, same shape. So it's a function which preserves the properties which rings have, which we want rings to have. So, for instance, 1 is 1, and multiplication it doesn't bother it, and addition doesn't bother it. And a ring homomorphism is a ring isomorphism, or just an isomorphism, if there is another ring homomorphism going the other way, which cancels it out. We will see in the next slide that there is an alternative definition, which is somewhat nicer, because then you don't have to find an explicit one, but that's the definition which carries over to more general things. So I thought that I would put that definition in. You can see the category theory coming out. So an example of a ring homomorphism, there's a ring homomorphism from the integer to any ring. In fact, there is precisely one, because 1 has to be 1, and any integer can be just 1 plus 1 plus 1, etc. So there's exactly 1. And again, there's exactly one ring homomorphism from any ring to 0, because everything gets mapped to 0 and there's no real leeway for the outputs. So a thing which you might want to know is okay, I will introduce these and then I will introduce why you might want to know it. So, firstly, kernel and image. Image, why you would want to know the image comes immediately from the definition. It's the bits which are mapped to. The kernel, the word itself means seed, and that's because a lot of the structure of a ring homomorphism can be inferred by the kernel. So it's the seed of the properties of the homomorphism itself. But its definition is the bits which get mapped to 0. So within the within the homomorphism from R to 0, everything R is the kernel, or within the ones from N to from N to any ring, the kernel is just 0. So there's two properties which you can have. So a ring homomorphism is injective if the kernel is 0. What that corresponds to is the map just sends certain elements. It might not send it to every single element, but it sends the elements which things get mapped onto are unique. So for instance, n into q, not every element is mapped onto, but every element maps uniquely onto another. Whereas this isn't the case in maybe that field of two integers, so n maps onto 0, 1, 0, 1, 0, etc. Or z, not n. Is it n over there? No, it's not z. And a field and a ring homomorphism is surjective if it completely maps to everything. So it might map different things, but it maps to everything. So another trivial example is the maps to 0. Those are surjective. But there is a injective and surjective ring homomorphism from every ring to itself, given by R maps to R, which is called the identity homomorphism, which, yeah, it's defined. The alternative definition of a ring homomorphism is an injective and surjective map, which there's a it's less generalizable, that definition, but it's more computable, that one. So you can very easily compute, okay, is the kernel 0 or is it everything, or is it not 0? So I don't really know. So it's very easy to tell if a ring homomorphism is injective or if it is surjective by just going, okay, I have an S. Can I find a phi of R which goes to S? No? Then it's not surjective. Yes, it's surjective. Same with injectivity. Within actual practical calculations, this is fairly easy to properly define. So we next move on to polynomial rings, which will be our final stop in this video, which in good time. I thought it would be roughly the same amount of time. I was worried that I would blitz through it all, but I'm confident in my abilities to waffle. So, a polynomial ring is a ring of polynomials, which you might ask, what is a polynomial? Well, it is something which looks like this. It comes from the Latin many names, which doesn't give a good picture, but not a good picture, but it doesn't give a sense as to what it is. But it's anything which looks like this. But given any ring, you can add a independent or indeterminate variable onto that ring and expand that. So you have R adjoin X is expressions like this. That's the formal way of writing it, but it's expressions like this. Notably finite expressions like this, so you can't have 1 plus x squared plus x cubed plus x to the 4 plus x to the 5th, etc., going on forever. But you can have that stopping at every point, so x, or 1 plus x, 1 plus x squared, 1 plus x squared plus x cubed, etc. I'm not continuing that. This R adjoin X is itself a ring, which is seen here. So this is an element of it. This is f plus g and f times g are elements. What I would like you to do for next time is why is this, but also verify that f1 plus f2 f3 plus f4 equals f1 f3 plus f1 f4 plus f2 f3 plus f2 f4, i.e. verify that this is a ring. I will say verify that this is a ring by physically computing. Verify that these operations make R adjoin X into a ring. So we want addition to be commutative, there to be a inverse for everything, for an additive inverse for everything, for addition to be associative, for multiplication to be associative, and for multiplication to have an identity, and addition to have an identity, and finally, for multiplication to be bilinear over addition. Which, the last one isn't going to be fun to prove. I would prove it by induction if I had to. But just verify that it's the case. You don't have to prove it, so maybe give 2 or 3 examples of distributivity within maybe, yeah. So again, R is assumed to be a ring. So why is this? So yeah, f is a0 plus a, and then that gives your distributivity. And associativity, you're just going to have to get through that, go through it. But uh, the the terms here are pairs such that 0, 0, 1, 1, 2, 2, 2. There's each of the indices here. These are indexes. They all add up to 0, x to the 0, add up to 1, x to the 1, add up to 2, x to the 2. This is, again, an intuition for what's called a graded ring, but we will get there when we get there. So I will add in red graded ring. But for every element of our ring, there is a ring homomorphism with x going to r, or rather x squared going to r squared, or x cubed going to r cubed. These are within Z. So this is within Z, adjoin R. So Z join R. So the evaluation of 1 plus x at 1 is 1 plus 1 is 2. The evaluation of 25x minus 10x, 25 minus 10x plus x squared at 5 is 25 minus 10 plus 25 is 0. 10 times 5 is 0. And you can repeat this to get multivariate polynomial rings, which this is more accurate for the actual definition of a polynomial ring. So it's R adjoin x, but x is some vector x1, x2, dot, 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 where it's R1. All of these, this, but just again and again and again, to make a proper multivariate polynomial ring. So that kind of looks like elements of z adjoin x, y are like 1 plus 2xy plus y squared. That's an example. These are used all the time in algebraic geometry. These are one of the fundamental building blocks of it. Specifically, if R is an algebraically closed field, but usually the complex numbers is what it was designed for, but for other cases it's useful as well. So R adjoin x, where x is some vector like this. So you can have xy or x cubed y. So this approach of 0, 1, 2, 3, etc. doesn't really map onto it. So what you would be doing is 1xy, xy, x squared, y squared, x cubed, x squared y, xy squared, y cubed. So these are degree 3, these are degree 2, these are degree 1, this is degree 2, this is degree 0. In what's called the standard grading, but you can see why the powers add up to 2 or 3, etc. So that's another reason why we consider graded rings, but those are specifically Z graded rings, I think they're called, because it's 1, 2, 3 and not random elements of random groups, which I think I should introduce groups in the next time. But yeah, verify that this univariate polynomial ring, so specifically R adjoin x, forms a ring with this addition and this multiplication. And if you want to do less, then just think about why this comes about. So just break f and g apart into their constituent parts and then just use distributivity over and over and over again. So start with this bracket and then this bracket and then this bracket and then this bracket, etc., etc., etc. But I think that's probably enough for now. 45 minutes is well more than enough. But polynomial rings are massively used in algebraic geometry, especially classical algebraic geometry. Varieties cannot be defined, or affine and projective varieties cannot be defined without polynomial rings, which affine and projective varieties were the first things to be studied within algebraic geometry. I think that was in the 19th century by a lot of Italians. But yeah, this is entry 2 of my journal or diary.